Hi everyone, today's lecture is about the carbon cycle, and before I start I would like to take this opportunity to remind you once again that the Chasing Corals documentary is now posted. I hope that you all watch it in full and complete the attendance quiz for last week. And the deadline has been extended because the lecture videos last week were posted later than usual. But now we're back. We're back to our usual routine, and so I will post one lecture video on Monday and then another lecture video on Wednesday as well, right? So I'd like to start today's lecture by defining what a cycle is, right? When we're talking about whether it is the energy cycle or the hydrological cycle, we are talking about continuous exchange of matter between the different spheres, right? So when we're talking about carbon cycle, we are talking about the continuous movement and transfer of carbon between the different spheres, right? So it could be, for instance, when we're talking about the hydrological cycle, then we are talking about the continuous movement of water between the different spheres. For instance, we have the evaporation, then the water escapes the source in the form of water vapor, and then comes back to its original source in the form of precipitation as well. So when we're talking about the carbon cycle, it's no different, right? So, or we're also talking about the energy cycle. For instance, what we have is I have said this before. So the sun is the primary source of energy for our planet, right? But outside the sun, so our planet is more or less a closed system, right? So we do have, for instance, plants taking up carbon dioxide from the atmosphere and then making their own food, while animals rely on cellular respiration. So we do have this constant exchange of materials between plants and then the animals and then the rest of the species. So we have this constant exchange of carbon, right? So if I ask you why carbon is important, so the following reasons are one of the most important reason is carbon is actually the backbone of life on Earth, right? Everything we do in this planet, it's actually one way or the other related to carbon. So for instance, our civilization, economies, homes, and then even our bodies, they are made of carbon, right? So we really rely on carbon to sustain our livelihood as we know it today, right? So that's also a problem, as I'll discuss in the next slides. So why we are having these problems, for instance, like we've talked about in previous lectures, how the greenhouse gas emissions impact our climate in different forms, right? So so we actually, there is no way that like we can sustain life independent of carbon. But when we're talking about climate change in the form of like carbon dioxide emissions from anthropogenic sources, what we are talking about is actually managing this carbon, that extra carbon that we release to the atmosphere, right? So naturally, what we have is we do have different sources, right? We do have different sources of carbon. So we have like plants, biomass, and also industries, different forms of industries emitting carbon in the form of in different forms. For instance, when the plant biomass dies, release that it's entirely made up of carbon, so it becomes an important source of carbon, and that's usually emitted to the atmosphere, right? And then there is also, of course, a significant source of carbon that is also that's sourced from the ocean, as I'll come back to this point in the next slide, right? But It's very, very important to remember that the relative size of the major carbon reservoirs that we have are quite different. So, for instance, there is actually considering the amount of carbon that we have, what we have in the Earth's crust or the oceans. It is actually what we have in the atmosphere. It's considerably low, right? So we do have in the Earth's crust about 100 million gigatons of carbon that's already stored, right? And then the ocean or make up about like 38,000 gigatons, right? So we only have like roughly, these are estimates from 2016, we only have about 865 gigatons of carbon, right? So in a sense, so our atmosphere is the smallest reservoir, and so of course, and because of it, it's actually easiest to push around, right? So what we don't want, and for the sake of the climate, is actually piling up this number, right? Pushing the carbons that we have in the atmosphere to the higher number, like for instance to the levels we have in the land biomass. So that would have severe consequences and on the climate, as I will explain in the next slide, right? And so there are two forms of the carbon cycle. One is the fast carbon cycle. So we do have what I mean from fast carbon cycle is we do have this rapid exchange of carbon between the different spheres, whether it is the ocean, the atmosphere, or the top of the lithosphere. We do have this fast exchange of carbon between the different spheres. While what the slow carbon cycles involves what we call this process takes from millennium to hundreds of millions of years. So it involves the complete turnover of the ocean. So this is a very slow process. What we have is the slow transfer of carbon from the different spheres, right? So we divide these two carbon cycles based on the time they take to complete one cycle, right? So I'll give you one example. So for a fast carbon cycle, remember it is a fast exchange, right? So we're talking about days to a decade, right? So very fast processes. And but this one we're talking about from thousands of years, many thousands of years to millions of years, right? And the slow carbon cycles also involves a series of complex chemical reaction, right? So what this means is that we actually we do see a very consistent increase in the carbon dioxide levels in the atmosphere, right? So the slow carbon cycle, even if like it removes the carbons that's available in the atmosphere, it really takes a very long time. So it can't be used to. It's not in any way helpful to remove that carbon dioxide that's already available. We see that we have in the atmosphere, right? So for the slow carbon cycle, we really involves these complex processes where carbon in the atmosphere is slowly removed from the system, and then it is buried deeper in the ocean, right? But for the fast carbon cycle, again, this this exchange takes place in a very short period of time, right? So, for instance, look at what's happening here. So you have the months and the years here. So this is actually the carbon exchange that we see on a yearly basis, typically. So what happens is during the summer season in the northern hemisphere, like you see here outside here in Atlanta, it's getting greener, right? So so the plants are, the vegetation is very green in the summer season, so it takes up a lot of carbon dioxide from the atmosphere. While during the winter season, you would also see it here in Atlanta, but typically if you go higher, closer to the poles, what you see here, the vegetation dies during the winter season because it's just too cold, right? And then it's brought to life during the summer season. And then this actually impacts the carbon dioxide levels, like on seasonal, interseasonal, interannual level, right? So we do see, I'm showing you here carbon dioxide data, global carbon dioxide, mean atmospheric carbon dioxide, as recorded in one station that we have in Hawaii. So what you see here, of course, global carbon dioxide levels are rapidly increasing, right? So these are the change you see here are about 60, almost 60 ppm change over a 60-year period of time, right? So I'll show you how big of a change this is, and I'll put this into perspective in the next lecture when we talk about past climate change. But for now, just see that, like, we do see that this positive trend, very strong trend, that we see carbon dioxide levels are rapidly increasing, right? So what you see here also is these wiggles, right? So these wiggles are because of the seasons, because depending on the season where you're looking at, we do have vegetation changes, like whether it's winter or summer. And then this figure shows you that, like, carbon dioxide is because of the plantation, because of the vegetation types, the vegetation actually it's removed, and then we have this small changes because once during the winter season, for instance, in the northern hemisphere, what we have is it's pretty dry, and then so the plants are not, they don't really have the leaves, they're almost dead, right? And then they won't be able to remove that carbon dioxide from the atmosphere, right? So it also shows you that, like, how these thick forests we have in places like the Amazon or in other places in the tropics are very important. This is one of the reasons that we call the Amazon as the lung of the planet. Okay, and of course we do have, like, the ocean is also an important source of the carbon dioxide, right? So the ocean holds about 50 times more carbon dioxide than the atmosphere, right? So, and of course, what happens if we warm the ocean, if the temperature keeps rising, then it actually becomes more and more easier for the carbon dioxide to more and more easier for the carbon dioxide to escape the ocean, and then for the ocean to become a significant, it's already a significant source, but to become more significant source of carbon dioxide, right? And then that would then cause more additional warming. So that's one example of the positive feedback loop we've discussed in earlier lectures, right? And the other problem is that ocean acidification. Again, I'll come back to this point when we we'll discuss this point later in later lecture videos. But you also have it's already discussed. It's also discussed in the Chasing Corals documentary, and then you get the idea why it is becoming more and more of a problem. So what happens is that that extra carbon dioxide we have in the atmosphere, it's also becoming a source, and then that carbon dioxide ends up in the ocean, right? So what we have is that carbon dioxide being added to the system. So we do have, it tends to have, it makes the ocean water more acidic, right? So we do have this complex reactions at the end of the day, and it actually we have this the water, the H2O reacting with carbon dioxide, and then this complex reaction it ends up eating the carbonate ions that are present in the ocean, are also very important for the marine organisms to build their shells, right? So the ocean acidification, it's a major problem. But fundamentally, what we're looking at, the reduction in the pH of the seawater, right? And so we're looking at the reduction in the pH of the seawater due to the absorption of the carbon dioxide by the oceans, right? Because we do have those constant interaction exchange between the atmosphere and the ocean, right? So the ocean is also a source, and then it's also a sink of that carbon dioxide, right? So I just want to look at show you these differences in pH in ocean acidification. This was 1850, right? Was pretty much blue, so more or less like many, almost except tiny spot here. It's basically the pH of the ocean was about we can say this margin, but like close to 8, right? So, but what we have here is like, you know, the for the end of the century, this is what's predicted. So the ocean is becoming more and more acidic, right? And then this has a very serious serious consequence for marine life. So what happens is that, of course, when that carbon dioxide is being added to the oceans, or we have this complex reaction takes place. We have carbon dioxide that's being added from the atmosphere. Of course, the ocean is H2O, that's water, and then we have this freely available carbonate ions. These needs to be freely available for the marine organisms to build their shells. So they need this carbonate ions. So what this reaction does is that instead of making this carbonate ions freely available for those organisms to build the shells on, it ends up taking these carbonate ions, and then it causes it actually removes these carbonate ions from the system, and then instead what we have is there is no more material available for those marine organisms, different marine organisms to build their shells, right? So that means, for instance, if they're not properly, if we're not able to, for instance, humans, if we're not able to properly really generate our skin, we can't survive here in this planet, right? It's the same is true for the different forms of life we have in the ocean. If they are not able to build or generate their shells, then they can't survive, and then ultimately they die, right? So this is a serious problem. So we do even see change in what we call the aragonite saturation state, which is a measure of the thermodynamic tendency for the mineral calcium carbonate to form or to dissolve, right? If we don't really have the calcium carbonate, it really has serious consequences for marine life in the ocean, right? So what this causes is that, well, like if we keep pumping the carbon dioxide to the ocean, and then that keeps eating away the free carbonate ions that marine organisms need to build their own shell, right? So this is a serious problem, right? And so here I'm showing you the change in pH between 1751 to 1994, right? So if you, what we see here is it's actually we are more pushing to the ocean to become more acidic as time progresses, right? So a different form of visualizing the data here is, for instance, if you look at what's happening. So we do see the rise in atmospheric carbon dioxide. Of course, like I showed you earlier, it's the same data sets. And then we do see the seawater partial carbon dioxide. So it's a measure of the amount of carbon dioxide that's being added to this seawater, to the oceans. Also see an increase. We do see the same trend, what you see here in blue, and also look at what's happening to seawater pH. So this tells you that like the ocean is also becoming more acidic. But so And then the other problem is it's actually the warm ocean. We know that the warm ocean holds less dissolved carbon dioxide, right? So how do we know that? For instance, think about if you're for instance drinking Coke, right? And so you'd like it to be cold, right? There is a reason, because if it is just like if you leave it open and it warms up, so it wouldn't be able to absorb that carbon dioxide, so it wouldn't feel the same, right? So the same way, the same concept applies for the warm ocean, right? So if as we keep warming the ocean, it becomes like a significant source. It becomes, and then it really starts adding more carbon dioxide to the atmosphere as well, right? And we don't want that, but also then we do have the high amount of carbon dioxide is already being emitted to the atmosphere, and then we still have, even if the ocean is an important source of carbon dioxide, it also we do have the same interactions causing ocean acidification as well, right? And so if we keep pushing of course, if we keep pumping carbon dioxide to the atmosphere, the most important point here in this lecture is that, remember, as we add more carbon dioxide, we are also in a way adding more carbon dioxide and warming the ocean as well, right? And then that causes more, makes the ocean more acidic. But the most important issue here is that, of course, if the ocean is more acidic, then through a complex chain of reaction, then that added carbon dioxide eats away the carbonate ion that is critical to sustain marine life in the ocean, right? But we will come back and discuss this point, this concept again and again throughout for the rest of the lecture, because this is very, very important, right? And on Wednesday, we'll talk about, I'll put this into perspective when we're looking at past climate change, right? So we'll compare the rate of change we have today and what we see today. And then if we can find anything similar in the paleo record, right? All the best, guys.